Parkinson's disease is among the most enigmatic and devastating neurodegenerative disorders known to modern medicine, characterized not only by its visible motor symptoms, but by an invisible, progressive breakdown of neural harmony. Parkinson's presents a uniquely multidisciplinary challenge, one that bridges biology, systems theory, and informational dynamics. The loss of dopamine-producing neurons is only the beginning of this disease. Beneath the clinical tremors and rigidity lies a deeper story, the gradual erosion of neural timing, coherence, and response. And unlike structural brain damage that presents suddenly, Parkinson's unfolds like a slow blur, erasing the fidelity of neural communication piece by piece. My name is Yuvraj Arora, and I am a grade 12 student at Sun City School International Academia, Gurugram, India. Today, I am presenting a project that was born not only from academic curiosity, but from a personal necessity. Titled Modeling Parkinson's Neural Dysfunction via Coherence Decay, this research represents an attempt to go beyond surface-level characterizations of Parkinson's and to interrogate the fundamental physics of neural signal loss. My point of origin was actually not from a textbook or, let's say, a lecture. It was actually by watching my grandfather gradually lose his control over his body, voice, and identity. And while the clinical answers felt insufficient, I hope that physics, and particularly the mathematics of coherence, might offer a more principled lens through which to interpret what I witnessed. So, my personal motivation. My grandfather passed away 8 years ago following a prolonged struggle with Parkinson's disease. By coincidence, or perhaps a kind of poetic symmetry, today would have marked his 85th birthday. This project, though grounded in equations and models, is ultimately a memorial of sorts. It reflects my attempt to understand what precisely was happening in his brain when movement became slow, when speech became fractured, and when his responsiveness that once animated him began to recede. Rather than to accept Parkinson's as a fixed list of symptoms, I chose to model its dynamics, to ask what exactly happens, but how and also why, through the lens of physical systems. The result is a simplified computational model designed to capture one of the most subtle yet critical aspects of Parkinsonian dysfunction, the degradation of signal coherence over time. By adapting the classical Fitz-Naguma model, and introducing a time-decaying input inspired by quantum decoherence, this research offers a minimal yet tunable simulation of how a neural system may lose its ability to respond deterministically and predictably. The objective is not to prove a biological truth, but to create a conceptual bridge between neuroscience and physics, between synaptic failure and informational decay. In doing so, this model becomes a tool for exploring degeneration as a process and not merely as an outcome. So, let's talk about Parkinson's for a bit. Parkinson's disease is commonly understood as a consequence of dopamine depletion, a neurochemical deficiency caused by the death of dopaminergic neurons in the substantia nigra. While this explanation holds clinical validity, it only scratches the surface of the disorder's complexity. Beneath the biochemistry lies a systems-level disruption, the progressive breakdown of coherent signaling across brain regions responsible for motor control. Neural circuits involving the basal ganglia, thalamus, and motor cortex do not merely transmit information. They orchestrate motion through synchronized feedback loops. These loops depend not just on signal presence, but also on signal precision, on timing, rhythmicity, and phase coherence. Parkinson's, therefore, is not solely the result of diminished input. It's the deterioration of structural communication within the highly sensitive network. In healthy individuals, this network exhibits high signal fidelity, the brain's capacity to transmit clear, temporally consistent commands between motor centers. This fidelity enables the fine-tuned regulation of movement, walking, speaking, even blinking in rhythm with our intentions. However, in Parkinson's, this communication begins to degrade long before full neural loss is observed. Misfiring signals, temporal jitter, and reduced gain slowly accumulate, eventually manifesting as visible symptoms. The pathology becomes not just one of silence, but of discord. This perspective reframes Parkinson's not as a binary system of functioning versus failure, but as a continuum of informational collapse. a process whereby once harmonious loops devolve into noisy, asynchronous remnants of their former synchrony. So let's actually think of a thought experiment, right? So to conceptualize this breakdown, consider the analogy of an orchestra performing without its conductor. In a typical ensemble, musicality arises not simply from each instrument playing its part, but from the alignment and timing, intensity, and rhythm. Now let's remove the conductor, right? And though the instruments may still function, the unity dissolves. Some musicians lag, others rush. Cues are missed, harmonies disintegrate. In this metaphor, the conductor represents regulatory neurotransmission. The musicians are the neurons, and the score is the encoded intention of motion. Parkinson's, viewed this way, is not merely a muted orchestra. It's an ensemble playing out of sync, where structural capability remains, but functional coherence erodes. This analogy is not merely a poetic exaggeration, actually. It aligns closely with what empirical data shows. Electrophysiological studies of Parkinsonian brains reveal disrupted oscillatory patterns, particularly in the beta frequencies that mediate motor control. Synchrony collapses, and the phase relationships between different cortical and subcortical regions become erratic. The result is not merely a loss of motion, but a loss of the timing architecture that underpins motion itself. Muscles no longer respond consistently to central commands, not because the commands are absent, but because they arrive out of phase, too weak or too late. This collapse of temporal fidelity is the specific dimension of Parkinsonian dysfunction that a model seeks to isolate and then simulate. Now, let's discuss the term signal fidelity, which is key to Parkinson's. The term signal fidelity refers to the integrity and clarity with which neurons transmit information across synaptic pathways. It's not sufficient for neurons to merely fire. They must do so with precision as well, timed correctly, with adequate amplitude, and within a coherent network structure. In Parkinson's disease, this fidelity erodes gradually. Intriguingly, electrophysiological studies suggest that degradation in neural timing and coordination often precedes the extensive death of dopaminergic neurons. In other words, the neural system begins to lose function long before structural failure becomes pronounced. This insight shifts our focus from cellular morality to informational decay, as though the brain forgets how to communicate before it forgets how to exist. To illustrate this, consider the analogy of a photograph losing its clarity. One need not erase pixels to render an image unintelligible. One need only blur them, right? So, similarly, in Parkinson's, the brain does not need to entirely cease firing in order to malfunction. It simply needs to distort its internal signaling enough that motion becomes unreliable. The problem is not absence, but distortion. Now, classical neuron models, such as the Hodgkin-Huxley framework and its simplified counterpart, the Fujii-Nagumo model, are foundational in computational neuroscience. They describe how neurons respond to external currents by modeling voltage dynamics and recovery mechanisms. However, these models often assume that external inputs remain stable over time, which does not match Parkinson's. Under these conditions, a neuron's behavior remains predictably periodic or excitable, depending on parameter values. This discrepancy highlights a key limitation of classical deterministic models. They do not accommodate systems that decay in function despite constant simulation. Parkinson's progression is marked not only by sudden disruptions, but by a slow and inexorable loss of responsiveness, a phenomenon that requires a fundamentally different mathematical treatment. Recognizing this gap, I pose the following question. Could we simulate the progressive failure of neural responsiveness not by adding noise or adjusting thresholds arbitrarily, but by modeling the time-dependent degradation of input coherence itself? This led me to an unexpected source of inspiration, quantum physics, where the concept of decoherence captures precisely the sort of collapse, an elegant mathematical tractable decay of information over time. So, the pivotal idea in my research is that neural deterioration in Parkinson's can be conceptually and mathematically likened to coherence decay, a phenomenon studied extensively in quantum mechanics. In quantum systems, coherence refers to a quantum system interacting with its environment and then losing its quantum state. It becomes classical. Though the brain is not in any literal sense a quantum system, the formal mathematics of decoherence provides an elegant model for simulating how informational integrity diminishes over time. The parallel is compelling. In both cases, we observe a deterministic, exponential loss of structure, not randomness, not chaos, but a predictable unraveling of system coherence. This insight reframes the original modeling challenge. Rather than injecting noise into the neural model or randomly varying parameters to system failure, I sought a more principled, physically grounded mechanism to embed time decay directly into the stimulus itself. So, to build a model around this framework, I employed the Fujii-Nagumo model, which I actually discussed previously, a reduced two-variable abstractation of the more complex Hodgkin-Huxley equations. FHN models the essential dynamic of neuronal excitability through two components, a fast variable, which is V of t, representing membrane voltage, and a slower variable, W of t, functioning as a recovery mechanism. Together, they simulate how a neuron fires, recovers, and resets over time. The mathematical elegance of the model lies in its dimensional simplicity and its interpretability. Its phase space yields limit cycles that represent stable and periodic spiking, a kind of dynamic heartbeat for the neuron. This makes it ideal not just for simulation but for analytical manipulation. Unlike the full Hodgkin-Huxley model, which involves numerous conductances and also gating variables, FHN abstracts the core excitable behavior into a form that is both visually intuitive and computationally traceable. This choice was deliberate because as a high school student, I don't have the capability to currently understand the Hodgkin and Huxley model because it requires high mathematical skills. While the standard Fujii-Nagumo model provides a robust framework for simulating periodic neuronal spiking, it assumes that the external input current is constant over time, as we discussed previously, unchanging and undeteriorated. This assumption does not hold in Parkinsonian contexts, where the same input signal, biologically speaking, becomes less and less effective. To simulate this observed decline in neural responsiveness, I introduced a deterministic decay mechanism, not in the neuron itself, but in the stimulus it receives. Crucially, this decay is not stochastic, nor the result of synaptic noise or fluctuating thresholds. It's a predictable, structured loss of signal effectiveness, akin to the exponential decay of coherence in open quantum systems. So this is our coherence term. This leads to a key conceptual move, right? Our coherence term is C of t equals to e to the power minus lambda t, right? Here lambda functions as a single tunable parameter governing the rate of information loss. This term borrows directly from the formalism of quantum decoherence, where off-diagonal elements of the density matrix vanish exponentially due to environmental interaction. In this model, the effect is analogous, right? Over time, the same external current evokes progressively weaker spiking activity, not because the system has changed in structure, but because the effective coherence of communication has degraded. This is a neuron not responding, less because it's damaged, but because the incoming information is gradually losing its interpretability. So this is our modified model now. With this framework in place, the modified Fujii-Nagumo model becomes a powerful tool for simulating functional degradation in neural excitability. The governing equations are now written as what's on screen right now. What has changed here is quite simple actually. We have preserved the geometric structure of the original FHN equations, maintaining all intrinsic neuronal dynamics, but introducing a time-dependent variable to the external stimulus. This single exponential decay term effectively injects the dimension of time and coherence loss directly into the system's input-response behavior. What makes this modification particularly powerful is its interpretability. The decay constant lambda becomes a variable analogous to increasing synaptic desynchronization, decreasing dopamine modulated gain, or rising entropy in the motor control loop. While this model does not claim that the brain undergoes quantum decoherence, it borrows the mathematical structure of decoherence as a metaphor for biological decline. The exponential decay function thus becomes a proxy for informational entropy, capturing how a brain may fail not by misfiring chaotically, but responding less and less coherently to signals that once gave proper motor commands. So let's discuss lambda, which is our actual parameter. The coherence decay function introduces a single continuous parameter, lambda, which governs the rate at which the external stimulus loses effectiveness over time. In this context, lambda is not merely a mathematical coefficient. It functions as a marker for disease severity. A lower lambda corresponds to slower coherence decay, emulating early stage Parkinsonian conditions or milder circuit desynchronization. Conversely, a higher lambda value represents rapid disease. This parameter provides an elegant tuning mechanism. With no structural changes to the equation, we can provide an entire spectrum of disease trajectories by varying a single value. More importantly, the introduction of lambda bridges biological observation with theoretical modeling. It maps onto phenomena such as progressive beta band desynchronization, reduced synaptic gain due to diminished dopaminergic modulation, and increasing network entropy across the motor cortex basal ganglia loop. Each of these is a hallmark of Parkinsonian decline, and all share a common feature: a loss of synchrony in time-dependent neural signaling. In this light, lambda does not stand in isolation. It encapsulates a range of neurophysiological processes within a single mathematically traceable variable. This simplicity is what makes the model both accessible and extensible. One parameter governs the onset, progression, and collapse of signal fidelity in a way that's computationally clean yet biologically evocative. Now, this is the part where I had the most amount of fun while doing this project. So now let's discuss the simulations. I'm going to divide this into early time, middle time, and late time. So in early time, where t is small and c of t is approximately 1, the exponential decay function has not yet significantly diminished the input signal. As a result, the system behaves almost identical to the classical Fujinagumo system. Spiking traces well-defined limit cycles, reflecting strong coherence and reliable recovery dynamics. This corresponds to what is observed in prodromal or very early stage Parkinson's, where clinical symptoms may be absent. Yet, the neural symptom is already operating near the edge of vulnerability. In this state, the neuron's ability to fire, reset, and maintain oscillatory integrity is fully intact. The motor system, at least as represented by this simplified model, continues to transmit high-fidelity control signals. Now, let's come to middle time, where, as you can see, the signal is now deteriorating. As coherence begins to decline, when lambda becomes moderate, the system transitions into a state of instability. The input current, though still present, is significantly weakened by the decay term, leading to an increasingly unreliable neuronal response. This manifests as a dampening of spike amplitude and irregularity in interspike intervals. The once stable limit cycles in phase space begin to contract and spiral inward, indicating a loss of excitability. The system exhibits an internal struggle. It attempts to maintain its rhythmic spiking behavior, but lacks the coherence necessary to sustain it. Now, this is where it gets even more haywire. At late time scales, when lambda is near 0.001, the decay function approaches 0, and the input stimulus is effectively nullified. In this regime, the neuron fails entirely to generate spikes. Its membrane potential flattens, its recovery variable stabilizes, and its phase space trajectory degenerates into a fixed point or near static region. In simulation, this state is represented by the red wave, a nearly flat line indicating complete functional arrest. There are no oscillations, no limit cycles, no feedback loops, and the system has not exploded into chaos over here. It has quietly ceased to respond. Now, let's map my model onto the symptoms of Parkinson's, which are rigidity, tremor, postural instability, and bradykinesia. So, in the early stage, where signal fidelity remains high, we observe clean, periodic spiking, analogous to healthy motor control. As coherence decays, spiking becomes less consistent, both in amplitude and timing. This mimics the onset of tremors, which often appear as irregular but rhythmic muscle contractions, and bradykinesia, which manifests as slowed or delayed movements. In the final phase, spiking ceases almost entirely, mirroring rigidity and freezing, where patients lose the ability to initiate or sustain motion. The model thus functions not just as a simulation tool, but actually as an interpretive framework, translating signal degradation directly into symptom expression. Importantly, this mapping is achieved without introducing separate modules for each symptom. There is no distinct function for tremor, no subroutine for rigidity. Instead, all symptomatic behaviors arise naturally from variations in a single parameter, which is lambda. This suggests that the diversity of Parkinsonian symptoms may be different surface manifestations of a deeper, unified process, namely coherence loss within the motor signaling network. Now let's discuss the lambda spectrum. Let's say the coherence decay term actually varies in different conditions, right? So by varying lambda across a range of values from 0.01 to 0.1 and beyond, we generate a full spectrum of dynamic behaviors within the system. At very low values, the exponential decay is nearly imperceptible. The neuron remains active for an extended duration, resembling preclinical or early onset Parkinson's. As lambda increases, coherence erodes more rapidly, and the system exhibits intermediate dysfunction. Unreliable spiking, degraded timing, reduced amplitude. At high values, even brief simulation windows lead to complete flattening of the output, representing the severe motor deficits observed in advanced stages of the disease. This continuous access allows us to simulate, compare, and analyze diverse Parkinsonian profiles without altering the underlying model structure. The ability to fine-tune the disease trajectory by modifying a single parameter makes the model particularly useful for exploring hypothetical interventions or disease variants. It also mirrors the heterogeneity observed in clinical populations. Some patients progress slowly, with tremors that persist for years. Others decline rapidly, developing rigidity and akinesia within months. This variability may be conceptualized as difference in effective lambda across individuals. Differences in how quickly their neurocoherence collapses. In this sense, this model offers more than a visualization. It provides a language for thinking quantitatively about disease progression. So, a general understanding of lambda can be this. While lambda begins as a simple decay rate, its influence on system dynamics is quite nonlinear. The neuron does not degrade smoothly or proportionally as lambda increases. Instead, you observe threshold behavior, long periods of quasi-stability followed by sudden collapses in spiking activity. This reflects a broader truth in complex systems. Small changes control parameters can push the system across a critical threshold, beyond which recovery is no longer possible. In the context of neurodegeneration, this mirrors clinical tipping points, after which motor symptoms intensify rapidly and irreversibly. So as you can see on the screen, small lambda equals to resilience, system oscillates longer. Cross-critical lambda, rapid irreversible collapse, and this shows tipping points and not a gradual slope. While it also hints at phase transition-like behavior and could explain sudden symptom worsening in patients. Now, this is the modified phase space of the model. On the x-axis, we have the membrane potential, and on the y-axis, we have the recovery variable. In the healthy regime, this plot would show a closed limit cycle, such as this. Let's move back once. Such as this. It's all messed up over here, right? But in our model, there's only one cycle, right? One cycle. The cycle does not close. Instead, it spirals once or twice and dampens into quasi-stationary space in the previous one. The system is no longer capable of sustaining oscillatory motion. It has become dynamically rigid. What we're seeing is a neuron that's been robbed of its ability to fluctuate. And in Parkinsonian terms, that's precisely the motor state we observe: freezing, rigidity, and the inability to initiate motion. Now, once I modeled it in a minimal network, we simulate a minimal excitatory inhibitory network over here. Just two coupled neurons with coherence decay applied. The red line is the inhibitory neuron's membrane potential, and the blue line is the excitatory. Initially, we see a sharp response to both stimulus. High frequency firing followed by damped oscillations. But over time, both neurons exhibit progressive flattening of activity. This is the new network level analog of the single neuron collapse we saw earlier. Importantly, this inhibitory neuron, typically more robust, also declines, showing the coherence loss does not remain local. It spreads. This suggests that Parkinsonian dysfunction may not originate solely from damaged regions, but could arise from network-wide dynamical degradation. This minimal model captures a profound idea. Coherence decay doesn't just mute individual neurons. It erodes the capacity of networks to coordinate timing. And in motor functions, timing is everything. Now let's analyze the model because it's got its own strengths, limitations, and also possibilities. So, the model over here, it captures progressive, time-dependent collapse, matching clinical progression. Most importantly, it reveals nonlinear tipping points and links quantum-inspired physics to neurology in a biologically motivated way. It also scales conceptually to networks, hinting at broader implications in motor control and cognition. However, it omits neurochemical realism, no dopamine dynamics, no glial or mitochondrial modeling. There's no stochasticity, real neurons are noisy. The model doesn't yet simulate full motor loops or validates its outputs with real biological data from EEG scans, etc. It's also too abstract for clinical use as of now, which limits translational impact in the short term. But that abstraction is also a strength. It allows rapid extension. We could add dopamine modulation, model supporting cell degradation, or incorporate noise via stochastic terms. The framework could be scaled up to simulate multi-neuron loops or motor circuits, because as of now, we've only done it with a minimal network, which is of 2 neurons. And perhaps more importantly, it provides a theoretical bridge. If we can match this model's behavior to empirical EEG or fMRI data, we can start building predictive, physics-informed tools for diagnosis or treatment, like closed-loop deep brain stimulation that adapts to coherence decay in real time. So that was my presentation, and I'm open to questions now.